Have you ever just listened to a single guitar note and wondered, how does all that beautiful, rich sound come from just one little string? Well, it might seem like magic, but it's actually math. Pure calculus, in fact. Today, we're going to dive into how the wave equation can describe the incredible, intricate dance of a vibrating string. Let's get right into it.
So yeah, this is really the big question, isn't it? How can something so basic, just a taut string, create all the complexity we hear in music? The secret, it turns out, is in the physics of how it vibrates. And the language we use to describe that physics, that's calculus. All right, to crack this code, we have to learn the language. And in the world of vibration, the most important sentence is this powerful little thing called the wave equation. You can think of it as the rulebook that governs literally every single pluck, strum, and vibration. Okay, don't let the symbols freak you out. I promise. This equation is actually telling a pretty simple story. The part on the left, UTT, well, that's just the acceleration of any tiny little piece of the string, how fast it's speeding up or slowing down as it moves up and down. The part on the right, UXX, that's just a fancy way of talking about the string's curvature, how bent it is at that exact same spot. So what the equation is really saying is this: the more bent the string is, the faster it wants to snap back to being flat. That's it. That's the fundamental physics of a wave in a nutshell. Now, the thing about an equation this powerful is that it can describe any wave anywhere, which is cool, but we want it to describe our specific string. To do that, we need to give it some rules to play by. In math, we call these the boundary and initial conditions. They're what lock in the string's unique situation, where it's tied down and how it starts moving. So let's break these rules down. First up, the boundary conditions. These are super simple. They just say our string is tied down and can't move at its two ends, at position 0 and at its total length, L. Easy enough. Then you've got the initial conditions. The first one, f of x, is just the starting shape of the string at time 0. Like when you pull a guitar string back right before you let it go, that shape is f of x. The second one, g of x, is its starting speed. Was it already moving the instant we hit the clock? This function tells us exactly how. Okay, so we've got our equation and we've got our rules. Now for the really amazing part, the solution. It turns out that any super complex vibration a string makes is actually just a bunch of simpler, purer vibrations all added together. Seriously, it's like a symphony being built from individual simple notes. And this brings us to this mind-bendingly cool idea called superposition. What it means is we can take a whole set of these really simple, clean wave shapes, they're called normal modes or harmonics, and we can just add them together in the right amounts to create literally any complex motion we want. It's the blueprint for how the string moves. So let's tear this solution apart to see how it works. That formula looks intense, I know, but it's really just three simple ideas bolted together. First, you've got the shape part, that sign term. That gives us our basic building blocks, the fundamental note and all its overtones. These are the pure wave shapes. Second, you've got the vibration part. These A and B terms, they tell us how much of each pure shape to use and how they each wobble back and forth over time. And third, that big sigma symbol, that's just the instruction manual saying, add them all up. That's how you get the final symphony of motion. Okay, so let's see this mathematical recipe in action. What's the real-world difference between, say, plucking a guitar string versus striking a piano string? Well, it all comes down to those initial conditions we talked about. And believe me, they completely change the kind of music that string is going to make. Check this out. For a plucked guitar string, you give it a starting shape, right? But its initial speed is 0. It's not moving yet. Because of that, all those B terms in our solution just poof, they become 0. The math gets way simpler, and the sound you hear is created entirely by that initial pluck shape. Now, flip that for a piano. A hammer hits a flat string, so its initial shape is 0, but it gets a sudden jolt of velocity. In this case, it's all the A terms that disappear. The sound is determined completely by the speed of that hammer strike. Two different ways to start, two totally different sounds. And that right there is the key takeaway. The way you start the vibration, that initial shape and speed, is basically a recipe. It tells the string which of those simple, pure harmonics to use in its final sound, and how loud each one should be. It's what gives an instrument its unique voice, its timbre. Now, this is all fascinating for music, right? But the power of this idea goes so much further than just a guitar string. Understanding the wave equation is really about understanding the fabric of the universe itself.
And this is where things get truly profound. The exact same mathematical ideas, superposition, harmonics, all of it, that describe a vibrating string are also what we use to describe sound waves moving through the air, light waves traveling across the cosmos from a distant star, and even the quantum mechanical wave functions of tiny particles. It is one of the most fundamental concepts in all of physics.
So I want to leave you with this thought. If the rich, complex sound of a single string is really just a simple symphony of pure mathematical waves all added together, what else out there in our universe works the same way? What other complex things that we see every day are just a collection of simple harmonics, just waiting for us to figure out how to listen?